Alright, doing part 1 here of our class on chapter 6. Remembering here, the mechanism of our first reaction we've learned. We have a pi bond as our nucleophile, so that is our nuke. We have the hydrogen of HBr as our electrophile. We start our arrows at nucleophiles and attack the electrophile. Electrons move. The HBr bond breaks. That, of course, is a slow step because we're forming a carbocation. You can imagine we're traveling high up a hill to form an intermediate. The carbocation is the intermediate, which means it, of course, has fully formed bonds, but it's not very stable. It's high in energy. The last step is the electrons from the bromine come and attack the plus charge, and that, of course, is fast. But now this would be the nucleophile, and this would be your electrophile, the carbon of the carbocation. Every step of the way, asking yourself, what's my nucleophile, what's my electrophile? And that finally forms our product, alkyl halide. So the last step is a fast step. Again, noting transition states, intermediates. Transition states do not have fully formed bonds. Intermediates do. Transition state, good. So just kind of breaking it down overall, you're going to have a pi bond. That's our nuke, our nucleophile. And of course, something is sp2 hybridized here. We have an electrophile, it's delta plus, and we also have a nucleophile. Sometimes these are attached beforehand, like we saw with HBr. And then our final product, we have an sp3, two new sigma bonds formed. This is an addition reaction. We're adding something across a pi bond, an addition reaction. Now here's a little more of a breakdown of the mechanism. What can happen when we have an unsymmetrical alkene, That's what we talked about in class 1 and 2 here. Carbon 1 would form a carbocation that's a primary carbocation, This would form a carbocation that's a tertiary carbocation, which of course means it's bonded to 1, 2, 3 carbons, whereas this carbon is only bonded to 1, so it's a primary carbocation. So it's less likely that we'd go this route because this intermediate is higher in energy. So it'd be less likely for us to make that because that intermediate would be higher in energy. So if we only form one product, because we're only forming one carbocation, because this is the fastest one, the easiest one to make, and also this is the most stable intermediate. Versus here, this would be really hard to make, really high hill, and hard to make this primary carbocation. It doesn't have the stabilization, This has very less hyperconjugation than this. So you will not see this product. Breaking that down, something we already know. So a tertiary carbocation is the most stable. And if we talk about hyperconjugation, we remember that sigma bonds, 2 bonds away, are these hyperconjugation interactions. Any sigma bond 2 bonds away will make it more stable. So if you notice a tertiary carbocation, it would have 9 hyperconjugation buddies, as I call them. Secondary would have 6, primary would have 3, and poor old methyl would have none. So that makes it less stable. Remember, plus charge and electron density in these bonds help stabilize it. So here's a picture of a nice little electrostatic map. You can see it's really blue. That means it's very, very delta plus. Whereas, you put that electron density in those bonds, 2 bonds away, that can help stabilize that. One of my favorite pictures in the book is this picture of hyperconjugation. I think it's a beautiful way to see a sigma bond orbital, It's kind of off-center, So it's kind of helping out this empty p orbital, which is sp2, So it's planar, and this is sp3. So that sigma bond, whatever sigma bond, doesn't have to be a CH, there can help donate electron density, 1, 2, 3 of them, 3 hyperconjugation buddies there, Versus a methyl, which doesn't have any of that help. Another nice picture, hyperconjugation again. This just highlights the 9 buddies, the 6, the 3, and the 3 gets here too. So it doesn't have to be CHs. In this case, it is CHs, but just sigma bonds. Here's our carbocation. 1, 2 sigma bonds away. 2 sigma bonds away. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2 sigma bonds away. Any of those bonds, 2 sigma bonds away, can help stabilize that. And the more you have, the better. Difference in rate, talking about this again. So if you see a primary carbocation, that would of course be right there. Notice how it's higher in energy there. It also takes more energy, So it's going to form slower, and you're going to form less of it because it's higher in energy. Versus the tertiary carbocation, with more hyperconjugation buddies, it's a more stable intermediate, and it also forms faster. Right? Its delta G double dagger is also lower. Right? So more stable carbocations form more rapidly. Right? That makes sense. So we call this regioselectivity. Right? The difference in carbocation stability determines the products. Right? So if you can have a differentiate here, we have a primary carbocation or a tertiary, you're really only going to get the tertiary. You're never form a primary carbocation. Those are really hard to form. Right? So this reaction, we call this regioselective. Right? It's going to select for this region of the molecule. Regioselective. As in, it's picking this region, that carbon, versus this one. So it's selecting that one exclusively. So in this case, what product will be formed? Right now, here we have differentiation again, two different types of carbons. Right? This one leads to a primary carbocation. This one leads to a secondary. Now again here though, right, we said we don't want to form primary, we'd form the secondary instead. 6 hyperconjugation buddies, 3 hyperconjugation buddies. Right? I don't know if I like the way the book says that bonds the most hydrogen. I like to think about the carbocation stability. So here you can use with HI or HBr. Again, you're looking for the carbon that could form the most stable carbocation. So this one would form a tertiary carbocation, as with this one. Is just showing this with HI and HBr. So again, this is regioselective. Right? We're selecting for one region of the molecule instead of the other. Right? It'd be minor products, right? Minor products, right? So completely regioselective, highly and moderately. This basically, if you can form one other products, right? Because this would be a tertiary, this would be a secondary carbocation. Tertiary is more favored, but you could still form some of this. So that's regioselective. Remember, picking one region over the other. So why is the first one more regioselective? All right, if we look at this, the difference would be the two options. Here, one of the options is a tertiary carbocation. The other option is a primary. And this one of the options is a tertiary carbocation, and the other option is a secondary. So what that tells you is the difference between tertiary and primary is great, to the point where you only get this. You're not going to form, the primary one. Right? So this is more regioselective because you're getting more of this. Now the difference between tertiary and secondary carbocations is a little tighter, so you can get a mixture of products. But the tertiary one will still be the major one, right? So it's not necessarily this one's more regioselective than this, just because the difference in carbocation stability. If I were to draw it, I would say tertiary is here. It's greater than secondary, but secondary is a lot greater than primary, right? So you can still get a mixture of these, even though one would be major, one would be minor, versus tertiary to primary, you only get one. Now another situation could arise where, if you look at these two carbons, if I said carbon 1 and carbon 2 here, they both would lead to a secondary carbocation. If I drew those out, carbon 2, or now we have a situation where we have a secondary and a secondary. Now this is going to be not regioselective at all, right? Because there's no difference in energy from these intermediates. So I'm going to get both a 50-50 mixture of 2-bromo and 3-bromo. Okay, so let's switch it up a little bit. What if we just have H plus in water now? What's going to happen here? Well, again, we have water. It's our solvent, I would say. I like to think of it as, right, if you have a giant beaker of this stuff, right, let's say this is A, this is a catalyst, this is B, this really is a catalyst, and then water's our solvent, C. There's a lot more C floating around, right? Right, we talked about concentration in the fishing analogy, and there's some A, and there's some B, and there's some A, and there's some B. Now, when we do a reaction, we want to find the best nucleophile and the best electrophile, the most reactive. So we talked about this. H2SO4 really is the same as H+, which is a really good electrophile, maybe the best electrophile. right? So that's going to react first. And let's say our pi bond attacks at H+, right? Because that's the best electrophile. Now what's going to happen is we're going to form a carbocation right here, right? We're going to form the carbocation here because that would lead to a secondary carbocation. We're going to form that carbocation, but the problem is this. There's a lot of C floating around. I bet C finding that plus charge is going to be more likely than, anything else. So let's take a look. So what happens here, right? And you can just redraw H2SO4 as H+, right? It's a strong acid, it completely dissociates, right? So pi bond attacks, right? You make this conjugate base, which again, though, right? If we think about our beaker floating in here, there's a lot of water, right? There's a lot of water. And some people might say, well, wait a second. This has a negative charge. This should be the best nucleophile. That's probably right. Maybe it is a good nucleophile. But what also matters is concentration. If there's one of these and 1,000 of these or 1,000,000 of these, the likelihood that this finds that is higher, right? It's higher. The water attacks, balance our charge. The oxygen cores have a plus charge, and we need to regenerate this because even though it doesn't say it here, this is a catalyst, and of course a catalyst needs to be regenerated before the mechanism is over. So the last step, this H+ falls off, right? And of course, H+ and H3O+ are the same, right? So don't confuse those two. H+ and H3O+ are the same, right? So now we've made, instead of making an alkyl halide, we've made an alcohol. Another example is if instead of having water in your beaker, right? So you have your big beaker, right? What if you had methanol instead? Same idea, no difference. There's just a lot of methanol floating around. So that's probably going to be your nucleophile in the second step. So pi bond attacks H2SO4, which is just H+. Again, make a carbocation. Again, there's a ton of this stuff around. Carbocation is a slow step. Ton of this stuff around. It attacks. We regenerate our catalyst, right? We get H+ again. What does the free energy diagram for this look like? So the free energy diagram for this would look like, right, if I said, right, so the arrows all indicate tops of hills. Right, so I would say it could look like this. You have your starting material. You have your slow step. We make our carbocation, which is high in energy. So if I labeled these as, right, these are the starting materials. This is intermediate A. This would be intermediate B. And this would be the product, right? And this is really the same as H+, right? Here's intermediate A. Go to a fast step where we make intermediate B, which then even faster yet goes to the product. So we have 3 arrows, which means we have 3 different transition states. We have 2 intermediates. Alright, good. Now life is not always so easy though. All of a sudden you're given this reaction and you'd say, okay, well I could either have a primary carbocation or I could have a secondary, right, if I was looking at this. But all of a sudden I see, how did the carbon get over here? If the number of my carbons, 1, 2, 3, all of a sudden my Br ended up on carbon 3. How the heck did that happen? And all of a sudden, right, how did that happen? Well, something must have happened. And the one thing that happens is, right, there's another couple more examples. Again, all of a sudden, looks like we were supposed to have, right, we could have a primary or a secondary, but all of a sudden it ends up on the carbon over here. So what's going on? So what's going on is a hydride shift in some of these. So what happens is when you form a carbocation, it will try to make itself more stable. And what that means is if there's a sigma bond 1, 2 bonds away that can move and literally move that element, it will if it forms a more stable carbocation. So in this case, you'd have a primary, secondary, so secondary would of course be favored. But if you notice, 2 bonds away, if I move this H, I would make a tertiary carbocation. So guess what? That's what I'm going to do, right? And I always I really got to lasso these guys, Really got to lasso them, and you got to show those electrons moving. And that H moves over there as well, right? The whole thing moves over. And when that does, though, now you have your tertiary carbocation. And then our same rules as before, of course, apply. Tertiary carbocations are more stable, and that's what you get. And guess what? This step right here, this shifting, super fast. Because a carbocation that forms wants to get more stable really fast, so it's going to do that super quick. So that's moving an H, move a methyl if it's 1-2 bonds away, if the resulting product is a tertiary carbocation. So again here, form our secondary carbocation. Right, this is possible, but how fast is this step? It's super fast. And what happens in this step? Right, these electrons in this bond take that carbon with it, that CH3 with it, and they shift over. They move over. Right, because of the product they make, then is a tertiary carbocation, which of course then is really stable, and that's where the Cl- will attack. All right, and we'll get our more major product that way. Now, be careful. This isn't always the case. Right? So this would be a primary, so we know that's bad. This would be a secondary. But now notice, here's our carbocation. There's no bonds 2 bonds away that gets us something better. Right? So let me just draw this out this time. Right? So this is this. Notice 2 bonds away, yeah, there are H's here. But if I were to shift this H over here, I'd also make another secondary carbocation. That's not any better. So carbocations only, the rearrangements only go downhill to lower energy, right? You go from tertiary to secondaries. Or no, sorry, you go from secondary to tertiary. You never do a lateral move. You would never make a secondary and then make another secondary. Nope, that doesn't happen. You can make a secondary and then turn it into a tertiary, right? But notice, again, it has to be 2 bonds away, 1-2 bonds away. I could move this, but it wouldn't make it any better, right? It makes another secondary, and that's not what we want to do. Keep working on looking at these. These are some difficult things to do, but it's really important.